All right, in this video, what I want to do is I want to talk about some material from 7.7, which is called Approximate Integration. And it turns out that some of the integrals that we're talking about, well, all of the integrals that you see in this course, you can evaluate exactly, finding antiderivatives using the methods that we've talked about in class. So that includes just regular substitution, integration by parts, trig substitution, partial fraction decomposition, and those are the methods that we've talked about. So it turns out that there's some integrals that even with those methods, we can't evaluate. So for example, if I look at the integral of e to the x squared from 0 to 1, there is no elementary function whose derivative is e to the x squared. So we can't find its antiderivative. When I say elementary function, what I mean is all the usual suspects. So polynomials, logs, exponentials, trig functions, inverse trig functions, hyperbolic trig functions, all of the usual functions that you work with are called elementary functions. And there's no elementary function whose derivative is e to the x squared. And so what happens, and the way that we can deal with this, is that we can actually just create a function whose derivative is e to the x squared using Calc 1 fundamental theorem of calculus. Okay, so part 1 of the fundamental theorem of calculus from calculus 1. And so, for example, what you could do is you could define a function, say g of x, to be the integral from 1 to x of e to the t squared dt. And then there you go. That's a perfectly valid function whose derivative is e to the x squared. But that really just kind of kicks the can down the road. That doesn't actually help you do any of the problems or evaluate anything. And so even though this is what often gets done, and then we kind of study this function and look at it, and you can figure out things from knowing its derivative, for example, in the mean value theorem. Anyways, what we can do instead is we can just approximate the integral. And so if I want to evaluate the integral of e to the x squared from 0 to 1, I have basically 3 methods to do that. We have the midpoint rule, which is actually something that we talked about all the way back in Calc 1. Okay, so the midpoint rule basically says if you were to take, so I'm going to describe it in each case for this function. Okay, so I'll just draw this picture over and over. But if I look at the interval from 0 to 1, if I were to graph e to the x squared, I know that that's roughly going to look like an exponential. And at 0, we're going to get e to the 0. So that's going to be 1. And at 1, we're going to get e to the 1 squared. So that's going to be e. And then it's just very roughly, I don't need to be exact here, but it's very roughly going to look like that, just exponential. When x is large, it gets bigger very, very quickly. But anyways, this is e to the x squared, roughly. And so while we can't figure out the area exactly, what we can do is we can approximate it to whatever accuracy we want. Okay, so we can have this accurate to 2 or 5 or 100 decimal places. Even if we can't spit out the number exactly and say it's square root of 2 plus 1 or whatever. So what we're going to do is talk about methods for evaluating that. And so the first one is the midpoint rule. Okay, and so the midpoint rule basically says draw the rectangles like you did in Calc 1. Okay, so we're going to take up our area. We're going to split this up into, say, n equal pieces. I'm going to draw some rectangles. I'm just going to draw a few. And then what you can do is you can take the height of the rectangle to be the value of the function at the midpoint of the interval. So for example, if I look at the midpoint here, it looks like that's about here, and the height will be there. Take the midpoint, and so on. And so if you were to zoom in really far, let's just zoom into one of these boxes here so I can do this correctly. The height of the rectangle is going to be the value of the function at the midpoint of the interval. And you're going to notice that we're going to be overcounting area here and undercounting area here under the integral. And the idea is that hopefully those balance out. Okay, it's not really any more sophisticated than that. Okay, so we take that rectangle, we add it up. Okay, and so the midpoint rule says that this integral, so in general, the midpoint rule, which I'm going to call MR, says that the integral of a function from a to b is going to be the width of each rectangle. So we're just going to add up a bunch of areas of rectangles. So we're going to add up the width of each rectangle, which is what we're going to call delta x. So remember, the generic setup here is that delta x is b minus a over n. N is the number of rectangles. And then this is worth, I think, another graph here. And if I were to have f of x, say from a to b, then we can split it up and we call a x1, the next one x, I'm sorry, we call a x0, the next one's x1, x2, all the way up to xn. Okay, so when you see the xi's, that's what we mean is, we mean these points down here where the function is, okay, we're kind of splitting up the interval into n equal pieces. Okay, so we go from x0 to xn. All right, and we're just going to assume that we're splitting it up into n equal pieces. You could do this if some of the widths are different than the others, but we're just going to assume all the widths are the same. And so the midpoint rule says that we're going to add up all these values times f of, let's see, x0 plus x1 over 2 plus, I'll write this in some notation in a second, plus the width times f of x1 plus x2 over 2, all the way out to delta x, which is the width of the last rectangle. We take the midpoint. So it'll be delta x times f of xn sub 1 plus x sub n over 2. Okay, so altogether, this is going to be delta x times the sum of f of x sub I minus 1 plus x sub I over 2. We're just taking the averages of each of these points, x0, x1, x2. So we're taking the midpoints with the average, adding them up. That's the height of the rectangle. And there we go. So that's what the midpoint rule says. And I shouldn't use equal, at least not with the first one, just that it's approximately that. Okay, and so that's the midpoint rule. Doesn't have to be any more complicated than that. We use rectangles. The height of the rectangle is determined by the value of the function at the midpoint of the subinterval. Okay, that's it. Next is the trapezoid rule. The trapezoid rule is, it's what it sounds like. We're going to take our function, okay, and what we're going to do is we're going to split up our region again, this time into trapezoids. So this will work a little bit better here. But what we're going to do is we're going to figure out if we take a point here, here, here. Okay, so we split up our interval, we figure out what are the corresponding values of our function, and then we make trapezoids. So we make straight lines. Just like that. Okay, so we make straight lines. That's a trapezoid. We figure out how do we find the area of the trapezoid. And it turns out that the area of a trapezoid, okay, so the area of the trapezoid is going to be, well, I guess I better draw a trapezoid. So we have A, B, C, and D. I've drawn it kind of symmetric, which maybe I should fix that. So here we have A, B, maybe the other side looks like that. Okay, just so it's clear that you can have the two sides being whatever you want, C and D. And it turns out, if we calculate this height H, the area of this trapezoid is going to be 1/2 H times A plus B. Okay, so that's the formula that we're going to look at for the trapezoid. Okay, so that's it. So A plus B over 2 times H. And so we're going to apply that in our case. The trapezoid rule here says that if we integrate from A to B, our function f of x dx, this is going to be approximately equal to delta x over 2 times, let's see, the first trapezoid we're going to have, let's see, f of x0 plus f of x1. And then we'll do this for each of the subintervals. So f of x1 plus f of x2, all the way down to the very last one, f of x sub n minus 1 plus f of x sub n. And what we can do is we can factor out all of the delta x over 2's. The only terms in this expression that don't get added twice, so you have f of x1 gets added twice, x2, all the way up to xn minus 1. The only terms that don't get added twice are x0 and xn. So what we'll do is we'll factor out delta x over 2. And then we're going to have f of x naught plus 2f of x1 plus 2f of x2, all the way up to 2f of x sub n minus 1 plus f of x sub n. Okay, so that's the trapezoid rule. Okay, and that's it. So all we're going to do with the trapezoid rule is instead of using rectangles, we use trapezoids. We got a slightly better approximation. And yeah, that's really all there is to say there. Okay, we'll do some examples at the end here. Finally, let's look at what's called Simpson's rule. And Simpson's rule is a little bit more complicated, but it's very interesting. So the way that Simpson's rule works is you're going to take your function. Okay, so we have our just generic function f from a to b. We're going to split up the area. And so we're going to split it just like before. And instead of using rectangles and instead of using trapezoids, what we're going to do is we're going to think about one subinterval. So let's look at like one width here. And I'm going to zoom in here. And it turns out that what we do with Simpson's rule is instead of using rectangles or trapezoids, we're going to use parabolas. And so what I mean by that is we're going to take 3 points. And as you probably remember, 3 points completely determine a quadratic polynomial, right? So 2 points determine a line, 3 points determine a quadratic. And so if we were to use a quadratic to approximate this function, you wouldn't get exactly a quadratic because maybe this isn't exactly a quadratic, but you get something that's pretty close. Okay, and so we get some sort of quadratic polynomial there. We do this for each of these. I think this might be easiest to draw on the last one here. So we get this point, and then we use the midpoint. And so we're going to get something that'll look probably like that. Let me try it one more time. Something that'll probably like that. And it won't be exactly on the line, but it's actually a really good approximation, especially as the width of the rectangles gets smaller and smaller. And then instead of approximating, instead of getting the area under the blue curve, we're approximating with the area under the green quadratics, the parabolas. Okay, and so that's Simpson's rule. And it turns out that the way that we do this with Simpson's rule is, and I'm not going to walk through the details of this. I'm not going to walk through the details. I forgot an S in Simpson's here. I'm not going to walk through the details of where these numbers come from, at least not right now. But it turns out that this integral from a to b is going to be delta x over 3 times the following quantity. Okay, and here it's important that n is even. This only works when n is even. That's not a big deal though. If you wanted to use 5 rectangles, then use 6 and you get an even better approximation. Okay, so there's no problem here. We're letting n go to infinity anyways, so who cares if n has to be even. So our approximation is going to be that this integral is approximately equal to delta x over 3 times f of x0 plus you get 4 f of x1 plus 2 f of x2 plus 4. So you keep alternating 4, 2, 4, 2, 4, 2. Until at the very end you get to a 4 and then 1 f of xn. So again, the coefficients here are going to be 1, 4, 2, 4, 2, 4, and then eventually comes back to 4, 1. Okay, and they'll be symmetric. Okay, so that's the coefficients. That's Simpson's rule. Sometimes this is called Simpson's 1/3 rule. Okay, so anyways, that's Simpson's 1/3 rule. There's Simpson's 3/8 rule, which is similar, but we're not going to get into that for now. So what I want to do at this point is I want to actually approximate. I want to actually go through and I want to evaluate a few things here. I'm going to actually save that integral of e to the x squared from 0 to 1. I'm going to save that for class. We'll do that one together, or you can try it now, but we'll talk about that in class. What I want to do is let's look at the integral from 0 to 1 of sine of x. I'm sorry, the integral from 0 to pi. Let's do it that way. Sine of x. And this is one that we could evaluate exactly, right? We might as well. We know that this antiderivative will be negative cosine of x. Evaluated from 0 to pi will be negative quantity cosine of pi minus cosine of 0, which will be 2. There we get negative 1 minus 1. The negative out front makes it a positive 2. So that's perfect. So we get a 2 there. Now, let's see what the midpoint rule, the trapezoid rule, and Simpson's rule all say. And we're going to use n equals 4 for all of these. Okay, so we're going to use n equals 4. So the midpoint rule says that, and I'm going to take our picture here. We go from 0 to pi. We have sine, which looks roughly like that. We know at pi over 2, it's going to be 1. And at 0 and pi, it's 0. Okay, and we're going to use 4 rectangles, or split this up into 4 regions. So from 0 to pi over 4, pi over 4 to pi over 2, pi over 2 to 3 pi over 4, and then finally from that to pi. And the midpoint rule says that we're going to take, so let me copy this picture so I don't have to redraw it every time here, but we're going to take our rectangles here, and the height of the rectangle is going to be determined by the value of the function at the midpoint. So we're going to get something like that. This is probably going to be symmetric here because sine is symmetric about pi over 2, at least from 0 to pi. And so we're going to add up these values. So the midpoint rule says that our integral, I'm just going to call it I for ease of reference here, but our integral is going to be approximately the width of each rectangle, so that's pi over 4, times, let's see, sine of pi over 8 plus sine of 3 pi over 8 plus sine of 5 pi over 8 plus sine of 7 pi over 8. And then let's plug that into a calculator. And I'll invite you to do the same. So we're going to get pi over 4 times we're going to add up the values. Sine of pi over 8, sine of pi, 3 pi over 8, and so on. And that will give us, turns out it's about 2.05234, something like that, 2.052. Let's just go to 3 decimal places. Okay, so we're off by about 0.05, okay, which is pretty good. So that's the midpoint rule. For the trapezoid rule, we're going to get same idea. And I copied this picture so I didn't have to redraw it. For the trapezoid rule, we're going to split it up into regions again. So same regions that we did. And think about the values here. And then we're going to calculate the area of those trapezoids. Okay, and so Here, you can kind of tell what's going to happen if we're going to get an area that's a little below 2, it looks like, because since the function is concave down, all the trapezoids are going to lie underneath the curve. So that tells you a little bit about what's going on there. So it turns out knowing the shape of the function, knowing the concavity of the function, I mean, tells you a little bit about whether you'll get an underestimate or an overestimate. And so here for the trapezoid rule, our integral is going to be the width of each rectangle divided by 2 times, let's see, f of 0 plus 2 times f of pi over 4, 2 times f of pi over 2, 2 times f of 3 pi over 4, and f of pi. And of course, f of 0 and f of pi are 0. So we don't really need to worry about that. But we're going to end up with, so we're going to add up f of pi over 4, 2 pi over 4, and 3 pi over 4. And so that's going to turn out to be It seems too low to me. Let me make sure I just did that right before we go on. But f of 0 and f of pi so those are both 0. So all we need is the rest. So we get pi over 4. Oh, I see I was off by my constant in front. So we get 1.89. Okay, 1.896. Okay, so actually we get a better estimate. Oddly, we get a better estimate with the midpoint rule than the trapezoid rule. And that was because we had a function that was completely concave down over this interval, meaning that all of the area, all of the error was on the same side, meaning that we knew we were going to get an underestimate because there were pieces that were missing. In contrast to the midpoint rule, where we were counting too much here, but we were missing a piece there, right? So those pieces kind of balanced out. Those pieces kind of balanced out and so on. Okay, so we had a more accurate picture with the midpoint rule than the trapezoid rule, which is not usually what happens. Okay, but finally, let's look at Simpson's rule. So Simpson's rule, we're going to get that our integral is going to be the width over 3, so pi over 4 all over 3, times, here we have 4 pieces. We're going to have f of 0 plus 4 times f of pi over 4 plus 2 times f of pi over 2 plus 4 times f of 3 pi over 4 plus f of pi. Okay, so we get that 1, 4, 2, 4, 1 pattern that we were talking about. And this is going to be equal to pi over 12 times the following. So we're going to end up with, and again, I invite you to plug this all into a calculator with me. This is going to be 4 times sine of pi over 4 plus 2 times sine of pi over 2 plus 4 times sine of 3 pi over 4. And again, the f of 0 and f of pi are going to vanish, right? Those are 0. And what we end up with is 2.005. Okay, so a much more accurate approximation here. I'm not going to draw the picture. I mean, I guess I could. I don't know what good the picture is going to do here, but remember the idea is that you're approximating each curve with a quadratic. So we're going to take each of these points where our rectangles are and take the midpoints. And then we're going to figure out the unique quadratic that goes through those 3 points. those 3 points, those 3 points, and those 3 points. Okay, so we got a quadratic polynomial there, and a quadratic there, there, and there. It'll look something like that. And then we calculate the area underneath each of these, underneath the green ones. So again, we're approximating that arc with a quadratic, calculating the area underneath. That gives us a much more accurate estimate of the angle. Okay, but that's it. So that's really all that we're going to talk about in this section. I'll give you 1 or 2 problems where we have to do each of these methods, and that's going to be the entire section. Okay, so that's approximate integration. All these ideas roughly are what's called numerical analysis. So numerical analysis is a branch of math where there are certain problems like these integrals or certain differential equations or whatever that you can't ever solve exactly. But what you can do is you can get them as accurate as you want. And so in our case, if we wanted to get a more and more accurate estimate, what we would do is we would take and increase the number of rectangles. And as the number of rectangles gets larger and larger, we can actually calculate the error and see that it goes and gets smaller. Okay, and so we can kind of measure exactly how much error we have. So if we want to be within 3 decimal places, we'll just make sure that our error is going to be less than, say, 0.001 or whatever. Okay, so anyways, this roughly falls into a branch of math called numerical analysis. Okay, but that's enough for